whole section on that, but I wanted to talk about, in particular, latent and specific heats. Okay? So when we're talking about the transfer of energy from one object to another, we're talking about heat, of course, and we express it by using Q. But let's take a solid, and we're gonna give it heat, okay? And that solid is going to absorb heat, and it's going to increase its temperature. How it's going to increase its temperature is by this equation. If you're wondering why I'm looking over into the corner, I actually have them all written on the edge of the board, just beyond camera range. Cm delta T. Now C is referring to the specific heat capacity, and that specific heat capacity is specific to the material. Okay, so water has a different specific heat capacity than ice in some cases. Well, in all cases, but specific heat capacity of iron is different than the specific heat capacity of aluminum. Those objects both can absorb energy and they can absorb energy differently. Okay, well, not necessarily differently, but more efficiently than some other objects. Okay, so like water and ice are great at absorbing energy, so their specific heat is much higher than, let's say, aluminum. Aluminum does a terrible job of absorbing temperature. It heats up quite quickly. Iron is another example of that. Copper is another example of that. That's why when you look at cooking equipment like pans and bowls and that sort of, well, not bowls, pans and pots, you're looking at material that's made out of either aluminum, copper, or iron, because they have terrible specific heats. It's really easy to raise the temperature of those objects, where other objects have awful specific heats, like water. That number is huge. It takes a lot of energy to pump into that system to get its temperature to change, which is good for us. I mean, you know, if we had very low specific heats for water, we'd have to expend we'd have to have a massive intake of energy to keep our body temperatures what they are. Never just on a tangent. Okay, so specific heat capacity is intrinsic property. That's the value for water. That's the value for iron. That's the value for whatever you're using. M is referring to the amount of that material, the mass of it. Okay, so the specific heat is referring to the amount of energy that can be stored in a single kilogram, where M is referring to the amount of kilograms that you have. So that's telling you this is how much energy per kilogram, this is how many kilograms I have when there's a constant T, or there's a T in there too. And delta T is referring to the amount of change in temperature that object is experiencing. So if I'm pumping in 1,000 joules of heat, the specific heat in the matter here is basically the amount of energy that's absorbing per Kelvin. This idea of specific heat per Kelvin, I mean, this right here, is going to translate into joules per Kelvin. Okay, where T is the change in temperature in kelvins. So energy in joules. This is going to be joules per Kelvin per kilogram, and obviously a kilogram. So this idea of joules per Kelvin is how much energy that can be stored per Kelvin. Okay, and then temperature. Specific heat. Sorry, I'm going off on randomness that I don't need to be talking about. Cool? So that's a specific heat equation. That's how much energy is required to raise it 1 degree Kelvin for that amount of matter with that property, that specific heat capacity. Cool? But this is just to take that matter and raise it up, okay, to a temperature. But once the object starts experiencing a phase change, we need to talk about a different property, and we'll talk about phase change or latent heat in the next video. All right, thank you. So now, using the idea